Hello mathematicians. In this video, we claim that the derivative of the function f at a is equal to slope of the tangent to the curve f of x at the point x equal to a. Okay, so let's see why it is true. First, you take 2 points x1 y1 and x2 y2 in R2. Okay, then if you look at the line joining these 2 points, given 2 points, you can always draw a line joining these 2 points, and so this is the line joining 2 points. Then you can calculate the slope of this line. Okay, how to calculate the slope of this line? Y2 minus y1 by x2 minus x1. This is the formula that we learned in school to calculate the slope of the line. Okay, so slope basically measures how steep that line is. Okay, if, for example, this second line is more steeper than this first line. Okay, now, so this is our formula for slope. Let's look at the formula for the derivative. Okay, so the derivative of the function f at the point a is equal to limit x tends to a f of x minus f of a by x minus a. So we want to understand this quotient. So suppose this is the graph of the function f. Okay, suppose, and this is my point a. Therefore, this point is a comma f of a on the curve. And so now I take 2 points to the right hand side. So if you take 2 points to the left side, the same argument will work. So, okay. So we want to understand everything geometrically. So if this point is x, if you go straight, if you go straight, this point is x comma f of x. Okay. We consider these 2 points x comma f of x and a comma f of a. Okay. Then these are 2 points in the two-dimensional Euclidean plane R2. So we can calculate the slope of the line joining these 2 points. So this line, basically, this is the line joining these 2 points a comma f of a and x comma f of a. By this formula, for this line, the slope is given by f of x minus f of a by x minus a. Okay, now we have understand what is this quantity. This quantity is this quantity represents slope of some line passing through some line in the two-dimensional real plane. Now we want to see what happens to this slope as x tends to a. Okay, now, so x should goes to a. So first we move x to x1. Okay, so if this is x1, now again we look at the line joining a comma f of a and x1 comma f of x1. Okay, assume that x has now moved to x1, eventually it is going to a. If you look at now these two lines, now this region bounded between the line and the curve, now it has decreased. For example, this is the, maybe I'll maximize it. So you see the area bounded between uh, the line joining a comma f of a and x comma f of x. This is that area. Now this area, the area bounded between the graph of f of x and the line joining a comma f of a and x1 comma f of x1, this is much less. Okay, so as you move towards a, this area going to decrease, or in other words, as you move close to a, what happens is this point is going to move here, and this line also keep change at each step. And when x reach a, if you can imagine the line will be like this. Okay, so that secant line will become tangent line to this curve. Maybe if I draw it properly, it will be like this. Okay, so when x approaches a, these lines at each point, these lines keep changing. At x equal to a, this line became the tangent. Okay, so sorry at each step, what we are doing, at each step we are calculating the slope of each of this line. Therefore, when this x reaches a, we get the slope of the tangent of the curve f of x at the point a. Okay, so that is geometric explanation for this quantity. Okay, so each of them represent the slope of a line, and as extends to a, these lines going to be the tangent line. Therefore, we get this quantity is equal to slope of the tangent to the function f at the point A. So this is the geometric interpretation of derivative of f at a point. Okay, okay, guys. So if you learned something new in this video, please click like button and share with your friends and subscribe to my channel. Thank you.